we start out with a triangle inscribed in a circle with a radius of 1. You can draw a line from the center of the triangle in the circle to the 3 vertices. Knowing that this is a complete circle with 360 degrees, you can divide these angles into 120, which is 360 divided by 3. And from there, you can split one of these triangles in half to get a right triangle with degrees of 90, 30, and 60. So you want to find the area of this triangle, which would be base times height divided by 2. And using sine and cosine, you can do this. So the sine of 30 degrees, which is opposite over hypotenuse, so h over 1 would be your height, and the base would be the cosine of b over 1, which is adjacent over hypotenuse. So the base is cosine of 30 and the height is sine of 30. So now by doing the base, which is here, times the height divided by 2 would give you the area of this small triangle. But however, there are 2 of these and 1 of these. So you would times that by 2 to get this one triangle here, and then timesing this by 3 to get the whole area of the triangle, and that would give you an inscribed area of 1.299. In the circle, there are 360 degrees, and there are 3 sides of the triangle. So by dividing 360 by 3, I get 120 degrees, which are my degrees right here. Now when I put this triangle over here and split it in half, I divided the 120 degrees by 2 to get 60 degrees. And this relates to this expression, which is 360 degrees of the circle divided by n, which was 3 sides, and then dividing that again by 2 when I split it in half. So when I can write this by saying 360 over n times 1/2, and that is equal to 1 and 180. So then 180 over n. And now this expression can come all the way over here into the formula for expression for area of polygon inscribed in circle, which is n times sine of 180 over n times cosine of 180 over n. And I can use this expression for however many sides. So in this example, I have 10,000 sides. 10,000, which is n, times sine of 180 over 10,000 times cosine of 180 over 10,000. And now simplifying that, I have 10,000 times sine of 180 over 10,000 is 0.018 times cosine, again, of 0.018. And that gives me an inscribed area of 3.142. Now we are going to find the area of a circumscribed polygon. So to do this, we first extend the line from the center of the circle to create a perpendicular angle to the sides of the triangle, which is 90 degrees. So extend each line from the center of the triangle to the vertices of the triangle, and knowing that this is 360 degrees, you divide it again by the number of sides n. However, there are twice as many triangles as the first problem, which is why you have a 2 at the bottom. This expression represents 60 degrees, which is right here, and if you simplify, is also equal to 180 over n. So using tangent of 60 degrees, you find the base of the triangle and multiply this by the height, which is 1. So tangent of 60 equals base. Because tangent of 60 represents 180 over n, you plug back in 180 over n to get tan 180 over n. Then you must multiply by n, which is the number of sides of the triangle, to get the area of a circumscribed polygon.
Now when we compare the areas for the circumscribed and inscribed polygons with n sides, we see a pattern. For the polygon inscribed in the circle, as the number of sides increases, the closer the area of that polygon is to pi. For the polygon inscribed in the circle with 3 sides, the area is 1.299, or 3 square root 3 over 4. you can see an increasing pattern with the areas, and by the time the polygon reaches 10,000 sides, the area is 3.142, which is very close to pi. With our circumscribed polygons, a similar pattern is shown. However, instead of having the areas of the polygon increase to pi, the areas of the polygon actually start off at a larger number and decrease to pi. So for the circumscribed polygon and the inscribed polygon, the more number of sides n you have in a polygon, the closer you will become to pi. The circumscribed polygon areas are decreasing to get closer to pi, while the inscribed areas are increasing to get closer to pi.